Okay, let's present from the beginning. Okay, so what is a multi-class classification problem? Now, it's simply like the name multi. It means it's a problem that involves you classifying more than two class instances. So remember the first one we've been looking at is binary, which is a true or a false, a yes or a no, and all that. So in this case, you're going to be looking at much more complex problem that is having maybe three, maybe four, maybe five. In fact, there are situations you can have even up to 1,000 classes for you to classify. You know, that will be so complex. So remember the first one we talk about, if you're classifying fruits here, you could see we have a banana, an apple, an orange, a lemon, pineapple, and all that. And then you feed it into the machine, you're supposed to classify them, for example, into three classes. You're having the watermelon on its own, the apple, and then the oranges. So in this case, you have more than one um, classes. So when you mapped them into the level set, the instance could map to more than one classes. So what we mean here is that suppose, for example, we have three class instances. You will see that now this X is a vector, meaning we have X1, X2, X3, X4, and so on and so forth. So it means that when we are mapping in this case, we will have much more than, let's say we had the first class is orange, like we shown, other one is pineapple, is watermelon, the other one is apple. Then let's say as we have other ones, we have so many of them. But however, there is a difference between multi-label classification and multi-class classification. Now, I think I discussed this extensively with one of my master student when he was working on his project. We talk about this issue of multi-level and multi-class. The multi-class means that the one particular class instance can map into several other levels. So it means that let me see if I could I could represent. Anyway, I wanted to show you guys on how to put it in an Excel, but it's fine. But what I want you guys to know here is that you could have so many sub classification despite you have just one instance. So let's say you had let me see. I'm trying to look for a very simple example. Let's say you have a book and the book has a different genre, or it could be classified as um, let's say biology or something, biology textbook. But that biology textbook has so many subsections inside it. It has the anatomy, it has the microbes, it has the systems. I don't know. I'm not really in those fields, so I wouldn't want to talk about what I don't really understand. But let's say it has so many subcategories inside it. The same way, you can belong. For example, we talk about Nigeria earlier on before we start the class. Somebody if you're looking at Nigeria and itself as a country, it's kind of one. But when you zoom into Nigeria, you begin to have so many other ethnic groups. So, in as much as I am a Nigerian, I belong to a subclass of, let's say, middle belt. I belong to in the middle belt, you go down to still split and split. But in the case of multi-class, we are not saying this I sort of ranking, or no, it's not the ranking. Rather, we are saying that one element or class in one instance can belong to so many classes at the same time. That's, I think, what we are trying to say. One instance can belong to several classes. But in multi-class, we're saying one class to one instance, one variable to one it's fine. One class to one instance, one class to one instance. Yeah, that's true. That's a way to say it. So it means if I have the futures, the futures can map to each classes that are there. But in multi-label, the future can map to several classes. Do you understand? It's sort of confusing, but they are not the same. So multi-label, one instance to several classes. Multi-class, one instance to one class, one instance to one class, one instance to one class. So if we have a picture of a cat, a dog, and a horse, and you're asked to map them based on their characteristics, you will classify them looking at those characteristics that are unique to them. But again, we can have a situation where you are looking at horse, but let's say different types of horses. So it's sort of, there is this overlapping in this case. So because you're not looking at, the classes are not independent of each other, rather they are kind of linking each other because the futures is mapping to them. And I think one of the very good areas we talk about some of these things is in causality, where you could have the cause and the effect. And then the cause could be so many random things that are instigating it to happen. So another thing again that you're going to likely also see is the ranking of the label. So in multi-class, when we talk about ordinal, it means we're ranking. Like in the case of this label ranking, this is a multi-class problem, but we are ranking it based on several things. A good example is maybe a military person. In military, you have so many classifications of soldiers. You have the private, the recruits, the private, the sergeants, the uh, warrant officer, the whatsoever, the lieutenant, the major, the captain, brigadier general, and so on and so forth. Now, if you're working with that kind of thing, and you are asked to predict, for example, if who is likely going to end up going to a war front or something between them, you are not going to treat that label as a normal categorical label. No, because now you have to put so many things into consideration. For example, maybe the private or the recruit are likely going to go to the war, maybe compared to the lieutenant or compared to the general or something. So you have to take note of the orders of occurrence of that particular target variable. But the same way you do that, you have to also take note when you are dealing with multi-level ranking. So first, there is a multi-classification problem. It's not the same with multi-level problem. Secondly, there is a multi-class level problem, which has to do with ordinal or ranking, meaning the way it happens. Then we also have the multi-label with ranking. So the same way, you have to look at it. For example, in the human body, you have so many organs, but they are all coming from the human body. But each of them do not perform the same roles. Maybe the cognitive function is being handled by the brain, the excretion and has its own role, the reproduction has its own role, all the organs are working for one body for different function. But now, when you begin to look at it, there are particular organ or system in your body that anything goes wrong with them, the person is likely going to die because the survival of that person is tied to that particular system. So that system, it means the role of that organ is much more of how do I put it, much more important than the others. But that doesn't mean the other ones are not important. But because of the proximity of of the life of that person, depending on that particular organ, you have to place that organ ahead of other ones. The same way, maybe you talk about infection. When I remember when the COVID-19 came in, we were looking at virus, how those virus, the latter of those virus, how the more um, dangerous the virus is, or deadlier the virus is, the more the chances of the virus surviving decreases. And stuff like that. So the ranking in multi-label is going to be tied to one instance, but the occurrences will be like the way we're talking about in the multi-class, meaning you have to look at the order at which these things are coming from. Although in this class, I'm not going to be talking about the multi-label, but I'll see if I can find an example of the multi-label. Maybe in the next class, I could show you guys how it looks and what it does, then you could understand how the differences actually work. Yeah, John, I think you want to ask the question.
Yes, Doc.
Okay.
I was looking at the lambda one. Are we regarding them like scalar? Are they scalar or like eigenvalue?
Yeah, these are eigenvalues, not we can still say scalar or something. They are, but because we are dealing with matrices in this case, so we can say they are eigenvalues.
Okay.
Anyway, I will find time to talk about the multi-labels separately with example in Python so we could see them very well. Yeah, you also want to ask another question?
No, sir. No, sir. So that was a mistake.
Okay, it's fine. So, so we say unlike binary class problem where there are two possible, here we have three or more outcomes. So let's look at a good example of the multi-class. We have the handwriting digit recognition. So in this case, an image of handwriting digit was presented to the machine to actually recognize them. Then we have 2, 4, 3, so it could, and these writings, it could be a kind of very difficult for the machine to spot it. For example, this 8 here looks more like 0, but you as a human, you could easily know this is 8, but to the machine, it may read it as this is not 8. The same thing, the way this 2 was written was not the same the way this 2 and this 2 was written. The way this 5 was written was not. So you could see there is this difficulty. Example, when medical doctors write, I don't know if they have changed, but normally when they write, it's difficult for you to spot their writing. So the same way, this kind of handwriting recognition problem was given to the machine to see if it could be able to pick. Another example which we looked in the previous slide is the fruit classification. For you to be able to identify what fruit is it and how and what it's doing. And there is a popular example which we'll be looking at shortly when we're looking at a practical problem, the Irish flower classification problem. When we have the Irish flower, you need to, there is a way you need to spot if it's the Iris setosa, if it's Iris vasticula, or if it's Iris veniginica. So, and you're spotting them based on using the shape of the sepal and the petal. So, classifying them could be very difficult, looking at the fact that they are all Irish flowers, but of different species. So that's a multi-class problem that it's also quite difficult because they are not the same. You can see the color seems to be different, although they are all purple, but this one is kind of light. Also, the shape of the sepal in the both case and the petals are different. Then, the same way we talk about using the algorithms on binary case, we could also use the same algorithms in the multi-class issues. But in this case, we will not be, the algorithm will still be treating it as though it's working with a binary case. And this is what the algorithm is going to do. The algorithm is likely going to be looking at one versus the rest, or one versus one, or even the softmax. So what this means is that the algorithm will take each of the class and compare them with each other. Or it will take one of the class, compare it with the two of the class. So you can imagine the same way we have 0 and 1, the algorithm will still be using that same technique to treat the multi-class. So the same approach, but different cases in this manner. So if we have 4 classes, what the algorithm will do now is to keep 3 classes, and then to take one class like a borderline, and then it will say this class, what makes it different from these other classes. This also makes it different. It will do, and then in some cases, if you are looking at 1 versus 1, it means it will pick each of the class, treat it as a borderline, pick another one, treat it as a borderline. So it will treat it like sort of binary problem, despite that it is a multi-class problem. Then we could also use decision tree, random forest, support vector, and neural networks. But I don't want to talk about neural network because we have not discussed it as a topic on its own. But you should have it in mind that it is a subset in supervised machine learning problem. The only thing that makes it unique is the fact that we'll see that in this case, we're mimicking the human brain, and then we're looking at adding layers or stacking layers on top of each other. So that makes it kind of complex than the previous supervised learning problems we have been talking about. So before I go into the unsupervised, I want to ask, do you have any question?
Yeah, no.
Okay, good. So that will bring us to the close for the multi-class. But I wanted to say something. Do you want us to go to the practical of the multi-class, or you want us to cover the unsupervised?
Can we see the practicals of the multi-class?
Okay, great. So what we're going to do now, we'll switch to that before we talk about the unsupervised. So again, you can pull this multi-class from the GitHub. I put the file in GitHub. So you could pull it from here. Repositories. Yeah. Yes, so the file is here. So you could just go to the GitHub to download it. So now let me copy the path and put it to. Okay, so you could download it from I'll put the link. So you can just this is how you just download it and then you're good to go. Great. So again, like we did in our previous classes, we will talk about the EDA. We'll talk about the prediction. We'll also look at the grid, and then we'll evaluate the model. So again, the data set we'll be using is it's 150 samples coming from the Irish flower issue, which we talk about Irish setosa, Irish versicolor, Irish venica also. Is it venica? I think these things, these botanical names we used to do in agriculture those days. It's kind of dreadful. Okay, so we have the features that we are looking at is the sepal length, the sepal width, the petal length, and the petal width. So this data set is a very popular data set, and the target variable, of course, is the flowers themselves, the species, the Irish setosa, Irish versicolor, and Irish venica. So we have 50 sample for each of them. So we do not have issues with imbalance in this case. However, there are situations where we could have issues with imbalance. So always know that this is also possible. So the challenge here is how do you identify these target variables or target classes, sorry, based on these variables? Because I showed you guys here, you could see they actually look alike. They did look alike very well, looking at the three of them. You see, they look alike. So we need to find a way to identify them based on their characteristics. So there is that challenge of separating them based on these features that we have. So based on that, you could see from here, you could deduce that the future importance is a critical factor that we must take note when we're doing. So as usual, load the necessary package. So if you have likely installed the pandas, the NumPy, the matplotlib, the Seaborn, and the sklearn, and so on, you are likely not going to have to do any installation because they are the same packages from our last class. So all what you need to do, you need to run them. And then the next thing we do is now this dataset is already in Scikit-learn dataset. So it's easy for you to load them. But when you load them, you have to find a way to convert it to PDF. And then, so you can see when we load them, we indicated which one are the features and which one are the target. So first you load them. The next, after you load them, you define which is X and which is Y. So you run this. So next we need to read it as data frame. So we read the X, which are the we said pd.data frame X comma columns equals to future names because we have already indicated the futures here and also the target. Then we define the df species to be the target. So you do that, and now, like I always say, have a way to explore your data set to be able to familiarize yourself with the data. So the f.head will help you to familiarize with the data. So you will see the futures are just 4 of them and the species. So it's very, very small future set that we have, but it's just for us to understand what's happening. So again, we run the df.info to see if there are missing observations. We don't have any missing observation in this case, which did make sense. So the next thing we need to do is to now visualize. Now remember, because the species is categorical, so you have to use bar chart. So again, we use that. But if you notice, I actually introduced some new plots here because I want you guys to have a taste of other kind of plots you could do outside the ones we have been doing. Now, this scattered matrix is a very good way to have a preview of your data set, especially when you have continuous variable. Remember continuous and histogram. You can easily plot them using scatter plot or histogram to see how the data points directions are or the distribution goes. However, you would also see that if you have a lot of futures, this is not a good option because it will be so large. So again, like I said, when you are having lots of futures, you have to be very, very strategic. Imagine if you have 100 futures, putting them here would be tedious. So you have to be very, very strategic when you're doing your visualizations. So again, but this is a good plot for you to see how the distribution of the data set also go, you know. Then another way again, I zoomed into one of this, which is the Scikit-learn and the petal width. We want to see the both of them happening together. So the Scikit-learn, which is here, and the petal width, which is this one. So it means it is this one that we zoomed into. So what I did, I want to show you that you could also increase the label size of the x and y variable, axis. You could see that for you to do that, you need the plt.tick params to do that. You could increase it to any size. If you like, if you say 50 to increase. Now, the reason I'm showing you this is because if you are producing manuscript, you have to be very, very careful because some of the manuscript, what we do, and I used to act as peer reviewer for some journals, and sometimes when I get manuscripts, it's very difficult for you to read the figures. We look at the quality of the figures, the quality of the graphs, or the figures the person did. Another thing we looked at is the front side. Is it really big enough for you to be able to read? I will show you an example if possible. No, it's fine. Let me see. I think I have a good example to show you guys here. Now, this is a figure that I'm doing for a poster presentation I'm going to be having in like a week's time. Now, if you notice this, if you have gone to conferences, you will know, you understand that a poster is very big. It's not going to be small. One of the things you could see here is the font size. You could see this size is 34. This size is 38. This introduction is 48, and so on and so forth. But when it comes to the figures, when I was designing this figure here, I have to make sure that I keep a font size that when they print it, I'll be able to it will be bold enough for anyone to read from certain distance. So there are figures that if you are in certain distance, you cannot read them, the font size, because they will be small. So take note of these things when you are plotting figures. Don't just display the figures. For example, if you put these figures on a paper, you're likely going to see they will become small when you shrink them. Okay, so make sure you take note of this font size when you're putting your script. So that's why I try to do this, so to show you that you could increase the font size. So another way we want to see this is, like, remember I said continuous variable, we use histogram. So we want to look at the species and based on the futures. So when you run this, you will see that the distribution of the sepal length in each of the species actually do vary. Satosa seems to have more higher, followed by Vasticular, and Virginica has very small one. So the same thing for the distribution of the sepal width. We seems to have Virginica seems to be higher compared to the other two. Then when we come to petal length, we see the Satosa seems to be maintaining high ones, and then it's kind of concentrated around this point, but these ones seems to be wider from 1 to around 1.5, and then this one is from around 2 to 2.5, stuff like that. So the insight here is that the petal length and width shows distinct distribution across the species, while the sepal measurements overlap more, suggesting the petal features may be more discriminative. So another thing we do now is to plot the correlation to see how the heat map is being distributed, with how if there are presence of multicollinearity. Again, we could see that the petal length and width seems to be highly correlated, about 0.96. While the sepal length and width, very quite weak correlation between them, but we could actually see a lot of correlation between the petal length and width. However, it's important to be in this case. Do we just remove it? So stuff like that. So again, we'll talk about that and we'll see how do we deal with that. So we say the petal length and the petal width are highly correlated. We have the correlation greater than 90, but we have 96, which may impact the model like logistic regression that assume future independence. So we need to think about how we could be able to deal with this and this whenever we have highly correlated variable. One option is, do you just drop one of the variable and keep one? Have you ever wondered why we don't used to have several world-best players in one particular team? I don't know if I may be wrong because I don't really watch football as such, but I remember there was this club. I think it was probably Milan or one of the club that used to gather all these world best players after they sort of passed they have reached some age. They go to that club.
Yes, it's AC Milan. It's AC Milan.
AC Milan, yeah. So you discover that with all these concentrations they have, they don't really win the trophies as such. So the reason is because these players will end up competing with each other. So that's the same when we talk about machine learning. When you have highly correlated variables, they drag each other down, and that impacts the performance of your model. So that's why you see models like logistic regression not doing well. Not necessarily because it's not a good model, but because sometimes when the features are highly correlated, it makes it not to be able to get any insight from this model because these models think one way. It's linear kind of thinking. So once there is some interruption, it becomes a noise to the performance. So another good way you could check the distribution is using pair plot. I do like this plots. It's a very nice way to visualize them in different colors, you know. So if you see the way the pair plots came out, you will see that we color it based on the species. So, like I said, when you are talking of the sepal length, their satosa seems to be high. So you could see in the pair plots, the distribution will just show you how it comes out. It's really nice, when you looked at it. And another thing again, you could look at it's how they colored around. There seems to be a lot of issue of linear separation between the satosa, between Versicolor and Vaginica. The two of them seems to be really, really, really struggling to identify them. But the satosa always seems to be easy to distinct from the two. So it means that these two guys here are quite similar to each other. If you see, they are always clumps around each other compared to this guy. This guy stood out, very distinct. And, so if it's a medical stuff analysis, we will try to say, okay, why did these guys, what makes make them unique? We'll now begin to investigate them to see why. So they say Satosa is well separated from the Versicolor and Vaginica, which overlap in some future pairs. So the petal length versus the petal width. This suggests the classification challenge is going to be between the two. Really, because you could see that these two are always struggling among between themselves. So we should take note of that. So the next thing we will want is the descriptive statistics. So again, we looked at the descriptive statistics, the mean, the standard deviation, the median, the mean, the 25 percentile, the 50 percentile, and so on for each of the characteristics in the data set. And you could actually do see some good difference. The Satosa is quite small. The 25% is around 4.8. Particular is 5.6, the other one is 6.2, and so on. And the mean, you could see the minimum for the both of them actually seems the same, 4.9, 4.9. So there is going to be that struggle between the two of them. Another way is we want to look out for outliers. Now, if you're interested in looking for outliers, the box plot is a very good way of visualizing it. And also there is another one called the rain cloud. It's also a very good plot that you could see. So looking at this, you could see that we don't really have an outlier. Maybe outside these few points that came out, we don't really see much outliers in the data set, but this is quite a very good representation of the data set. So we see few outliers exist. The petal features show greater variation between the species and the sepal feature. So another thing now is to go to the modeling phase. So the same way like we did, you separate it into 20%, training 80%, testing 20%. Now, I introduced something called Stratify Y. The reason is because although we do not have issues of class imbalance, but when you begin to have imbalanced classes, if you just leave it to the random state seed, it will select more of the dominant classes and leave out the classes that are less represented. But when you put the stratify, you are saying maintain the same ratio of that you did in the training set and the testing set. So that helps you to have identical training testing. But if you don't stratify, sometimes you may have high representation in training, less representation in testing, high representation in testing, less representation in training, and that could mess up with your data set. So that's why, especially when you have 3 or more, stratification becomes important so you don't marginalize one of the class the target variable that you're looking at. So take note of that when you're splitting. So the next thing, because of the issue that we're going to be having based on the collinearity that we spotted here, it's good you standardize the future. Because when you standardize it or scale it helps to read out the impact of multicollinearity. So to a large extent, you can overcome the multicollinearity when you scale. Not always, but it's another very good way of dealing with multicollinearity. So there are several scalar approaches. There is the min-max, there is the standard scalar, there is robust Scala and all that. There are so many of them, but the one that is quite popular and also the reason is because this is also robust to outliers, although not in all cases, but it's considered like a state of the art. So you could use it, but if you're not comfortable, you could also try or experiment with other ones. Like the min-max makes sense when you are dealing with variables that are having lots of, for example, when I am having lots of zeros and one, I'd rather prefer to use min-max because the variables are already almost on the same scale. So scaling them using the normal standard scala wouldn't make sense for me. So sometimes the min-max works better in some cases. So, but again, feel free to experiment each of them. So by the scala here help us to, transform. So normally you fit it for the fit transform for the training, but you transform alone for the testing. So take note of that. So we did run that. Then the next thing is to run the logistic regression. Remember, without the grid search. So we just fit it straight without the grid search. So the next thing you run this, you will see 93%, which is quite good. 92%. And you could see the model was able to detect the Satosa easily. Even though the testing said we just have very few, I think we just have 10 points, but it's fine. It's not a bad one. You can see that we actually detect it very well. And then this is around 0.9, 0.9. Like I said, the struggle would be between the two of them because they look so similar. So another way you could visualize it in this place, this confusion matrix, is to put it in a heat map format because the heat map will really tell you what's happening. So the confusion matrix, most of the time, what you look at is the diagonal variable. These are the correct ones that your model predicts. Then off diagonals are the ones that the model missed out. So if you look at the Satosa, you see that it gets it correctly. All the 10 of them it predicts to be correct. It did not miss anyone. But when you move to the other one, you will see that it got 9 out of 10 correctly. So it missed out this one and said it should belong to this one, even though. So this is because the both of them look quite similar. So the machine was struggling to find where this one belongs. Then the same thing when you do for the third one, Virginica also, you will see that it got 9 correctly and missed out 1. So you could see the confusion matrix really tells you a lot about what you got right and what you missed out. So especially when you are dealing with multi-class, like 3 classes, I think the confusion matrix is good. But when the classes begins to increase, sometimes it's kind of difficult to interpret it. Anyway, so the next thing we do is to run it with hyperparameter. We perform the tuning. So doing the model tuning, we check, we see that the C is 10, the penalty is, in this case is 1, which means lasso. And I could understand why, because there will be a presence of 2 futures struggling, the petal length and width. So lasso will likely kill one of the future and work with one of the future. So this one will now run it to C, and the lasso also said it is 93. Even after we did the tuning with the logistic regression having this lasso's ability, it still says it's 93%, which is nice. So the next thing we do is to visualize the ROC curve. Now the ROC curve is perfect. We have 100. But I will tell you the truth. In real life, I will never be comfortable with 100. I will always question my model, because 100, it's likely there is going to be issues with overfitting. So don't be excited when you have this perfect model. Always know that there is room for errors. Okay, so you can see this is 99, 99, quite a perfect model, but we, like I said, in real life. But I understand because when the testing said, we just have 10 points, so it's not really much, for us. But again, try to question it. So I think our time is up, but I want to see if we could just try to finish up this. So you run the random forest as well, the same approach that we use, in this case without the what do we call it, without tuning. So we have 90% the accuracy. So the random forest a bit decrease in the sense that you could see. So the logistic regression seems to fit the model much more than the random forest. So what we do next is to visualize the confusion matrix. Again, we could see we do not have problem with Satosa. It's very, very easy to spot, but we struggle with the second one, which we have just around 9, that's vernicola. And then when we talk about Virginica, we miss out 2. So we got 8 correctly. So random forest seems not to get everything right. But now let's see what happens when we tune the model. So now we perform the model tuning on the random forest. And then we're going to see if it's going to improve our model or it's not going to improve our model. Then again, we'll run it. I don't think this will take time because it's just 150 samples. So it's very small. So it shouldn't take much of our time. Great. So again, when we tune the model, it's improved from 90%, it moves to 93%, which is quite great. So another thing, again, ability of the random forest is the fact that we could be able to see the future importance. And the future importance will tell us which of the future are contributing highest in the model prediction. So again, when you run the feature importance, you could see the petal width has the highest, followed by the petal length, and then the sepal length and the sepal width are also there. And I think you could agree with me that these were the features that were competing among themselves. The petal length and petal width were competing among themselves. But because we standardize, they also seems to have a very good. So another point that you may want to try is to see if you could drop one of them and see if you can still get this performance. So if you drop it and see you still get this performance, you will know that one of them is not really helping. So, but naturally we see the petal width has much more uh, uh, importance compared to the petal length. But the two of them are the dominant, most predictive features compared to the sepal width, which has the least. So again, we could visualize the ROC curve to see what we have. So again, the ROC reduced. Satosa have good score, but Vasicula reduced to 94 and Virginica reduced to 97. So we didn't have a perfect fit like that of the random forest. So the question is, which of the features is most influential and why? So on your own part, you need to ask yourself why these features seems to be the best features that help us to spot these 3 species of the Irish flower. And then the classification did decrease in random forest. What must have caused this decrease? We have seen it that we actually start getting it wrong when we increase the complexity of the model. So something must be wrong. However, today I don't think I'll leave you guys without a hand-on exercise, which you guys will perform. Then in the next class, we could discuss this exercise from your findings. So you will replicate the same Jupyter notebook that we have done, but in this case, we are going to focus on the digit dataset problem. That's this dataset problem here. This one here. So that's what you guys will focus on. Then as your exercise, you will classify them for us to recognize, when we see a 1, what is a 1, what is a 2, and all that. So you will load the data set, and then you guys will repeat it each from 0 to 9, like we see here in this slide. Then again, you guys will do the same thing that we did. However, in this case, you will take note of the fact that we now have 10 classes, not 3. Okay, so the complexity have increased, and the size of the data set is now 1,797 samples. So it's bigger compared to the 150 samples we did. And then the data set is roughly balanced. It means there are some few ones that are not, but roughly, so in each class size, we have around 180 samples. So the core challenge is that there is high dimensionality because we have 64 features. The data set seems to be relatively complex compared to the Irish dataset. So, and the computation is going to be expensive, of course, because now we have 64 features, we have 1,797 samples, so it's quite big. Then another thing again is that this is a non-linear relationship because we are talking about pixels. But the emphasis I want to make here is that the reason